Confused about redox? You're not alone. So today I want to tell you about redox, so reduction and oxidation from like a biochemist perspective. So a lot of times when you learn about or you try to look up stuff about redox, you get things from like kind of a gen chem perspective, so like general chemistry, and you're talking about oil rig. Oxidation is loss of electrons, reduction is gain of electrons. But in biochemistry, typically instead of like gaining and losing whole electrons, what's happening is more like you're gaining and losing electron density. So like who's the electrons hanging out with more when you form a new bond. And so if you form a bond to like a hydrogen, the hydrogen's really bad at holding electrons, so you get to kind of get free electrons. Form a bond to oxygen, oxygen's super electronegative, it's going to pull in those electrons, so you're kind of like losing electron density. And so I want to kind of talk about these various topics and help you kind of get a more intuitive sense of redox in a biochemistry perspective. Some of the times this comes into place, some of the times how you can see if oxidation or reduction is occurring, how to determine like oxidation and reduction, like the numbers, not in terms of, I'm not going to give you any like shortcut formulas or anything, but just in sort of like an intuitive sense of like when you look at something, you're like, I don't see why this is getting oxidized or reduced. Then I want to give you a sense of like why it is, not just, oh, well, if you add these numbers up, you get blah, 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 you know? So, I mean, that stuff is helpful for getting you to pass a test, but when you're trying to understand biochemistry, I think it's really helpful to have this more intuitive sense of what's actually happening. And so I know I found redox to be like super confusing when I was learning about it, and I still get like mixed up in jargon sometimes. But so hopefully today's post can help you understand things. Plus there are dogs and poker chips and stuff. So yeah, let's take a look.
So here's a basic overview of like where we're going. So we can talk about oxidation and reduction. And we have this nice mnemonic we can use, oil rig. Oxidation is loss of electrons and reduction is gain of electrons. They go hand in hand because if something loses electrons, something else has to be gaining electrons. And so this explanation works really well when you're talking about things like metals and that sort of thing, where it's clear to see where electrons are transferring. In biochemistry, however, instead of whole electrons, redox in biochemistry is typically involving like gain and loss of electron density. So basically, when two atoms are sharing electrons to form a covalent bond, they might not share fairly. And so if they don't share fairly, then one of them is kind of like, if you were to form a bond to something that pulls away your electrons, something that's electronegative, then you are going to be basically losing electrons. And if you form a bond to something that is really bad at holding onto the electrons, so you can kind of pull the electrons towards you, now you're gaining electron density. And so we talk about like these bonds forming between these electrons, but really it's more like these electron clouds. And so when these atoms come together and like merge their clouds to form bonds, and if they're not sharing fairly, if they share fairly, then you don't have any oxidation or reduction. But if they don't share fairly, now you do, because something is going to be now pulling away your electrons, or you get to pull more of their electrons. So when you have like different bonds form between molecules and you have changes in what something's bound to, now you have the possibility of having an oxidation or a reduction change. And one of the ways that you can tell for that is something called you can determine the oxidation number, which is like the theoretical, like if these were to split up, where would the electrons stay and what would the charge be if they were to split up? And so we'll go way more into this, but I just wanted to give you a sense of where we're going. So if you have two atoms bond together, so we think of in biochemistry, if you think like, it can get really confusing when you're trying to learn about oxidation and reduction, like because you're typically taught in like the strict like chemistry focused sense. And so I'm not going to tell you about like all these like formula, like the tricks and stuff you can use to memorize oxidation numbers. I want to give you just like a sense of what's actually going on and how it comes into play in biochemistry and how you can get confused when things are happening with like protonations and deprotonations, which do not involve oxidation or reduction, because you don't have any electrons. Like a proton, like by definition, there's no electrons happening. And so those do not change the oxidation status. However, you often see that a reduction is accompanied by the gain of a bond to hydrogen. And so why is this? So it makes sense, like oxidation. Okay, gain a bond to oxygen, you get oxidized. Okay, that's cool. They make sense, right? That's because, so oxidation is a loss of electrons or a loss of electron density. Oxygen is super electronegative. This means it like hogs electrons like crazy. If it binds to something else, it's going to be hogging those electrons. And so if you form a bond to oxygen, say goodbye to that electron density. In that bond, the electrons are going to be hanging out more often towards the oxygen. They love the oxygen more. So you're going to be getting oxidized. So often, but not always, oxidation is accompanied by more bonds to oxygen. So maybe you're bonding another oxygen, or you're forming like a double bond instead of a single bond. And this is just because the oxygen is more electronegative. It's not because oxidation is like defined by a bond to oxygen. You also talk often that reduction, or the gain of electrons, is often accompanied by a gain of a bond to hydrogen. So why is this? Well, hydrogen, it is really, really bad at hogging electrons because hydrogen only has a single proton, and the protons are as we'll see, is like the source of the electron pulling power. So if you have a hydrogen, if you form a bond to a hydrogen, it's basically like getting a free electron, because that hydrogen is really bad at holding on to the electron. So even though you're also getting that hydrogen's proton, we're not talking about like real charges here or anything. And so we're just looking at electrons. And so basically you get a free electron, because the hydrogen, when you bind to a hydrogen, the electron from the hydrogen is probably going to hang out with you more. And so it's like getting free electrons. And so that's why the reduction is often, but not always, occurs with bonds to hydrogen, because the hydrogen isn't good at convincing the electrons to hang out with it. Hydrogen is not very electronegative. And so oxidation and reduction go together. And so the terminology, like, so hopefully I don't like accidentally misspeak like throughout the post here, because I'm like really, I often get jumbled up in my head, because basically if the thing that is gaining the electron density, so the thing getting reduced, had to oxidize something else to do so. So it's called an oxidant, or an oxidizing agent. The thing that loses electron density, so the thing that gets oxidized, had to reduce something else to do it. So it's called a reductant, or a reducing agent. And so we'll talk more about some like common biochemical reducing agents, such as DDT, BME, and glutathione. But that's just some of the terminology. And we're going to get into this idea of an oxidation number. But an important thing to know is oxidation number is not the same as a formal charge. The oxidation number we're going to talk about is like a theoretical charge that a molecule would have if it were to be in like a purely ionic bond, if it were to actually like, if the bond were to actually break, and who would the electron stay with, and what would the charge then be? So that's this concept of an oxidation number that I'm going to get into. And so I'll talk about things with dogs and then poker chips. And so hopefully the analogies won't get too confusing. It's just something that helps me think about things. So normally when you learn about like atoms and elements and all of this stuff, you get this like formal view of things. So you have atoms, so like individual in like units of elements, carbons, hydrogens, etc. So they're made up of these smaller things, these subatomic particles. So these positively charged protons, which are kind of like glued together by these neutral neutrons. And then you have this electron cloud whizzing around with them. And we can never predict the exact location of an electron, but we can define these kind of like places where they're more likely to be. And there's this helpful kind of like generalization structure type thing where you have it kind of like these shells of an onion, which isn't really how it happens. But it's helpful to draw them this way, because typically they want to have this like full outer shell of electrons. And so I'm not going to go into all of this here, but basically so this is like the formal view, but I want to kind of like introduce you to my way of thinking about things. So bear with me, I think it's kind of weird, but I find it helpful. So basically, if you think about the protons as dog walkers and the electrons as dogs, and those furthermost electrons, the ones that are furthest away from the nucleus, so from the protons, so from like the dog walkers, those are going to have the most energy. These are the valence electrons. They're furthest from the pole of the protons of the dog walker. And so the dog walker has like the least control over these. So, but different dog walkers, so like different elements, their protons, their nucleus has different pulling power. And we can describe this pulling power with a term called electronegativity. So atoms that are really electronegative have a tight pull over their electrons, whereas those that are not don't have as tight of a pull. And so how electronegative an atom is going to depend on several things. And so it's going to depend on how many protons there are. And so as you move across a row in the periodic table, you're increasing the number of protons. If there's more protons, it's like there's the dog walker is stronger. So it can pull tighter, or you can think of there being like multiple dog walkers working together, like in the same, like tied together, like holding the leash. However, it helps you to think about it. But basically they can pull tighter. And so they're more electronegative. You get this trend of increasing electronegativity as you move across the row in the periodic table. As you move down a row in the periodic table, though, even though you are increasing the number of protons, so you're increasing the strength of the pull, from that perspective, you're actually getting farther and farther away from the nucleus. So even if they're like pulling harder, then the rope is like all the way farther out, so it's harder to keep a pull on those far away electrons. You get this sort of shielding effect from the inner shells of the electron, are kind of like shielding the dogs on the very far end of the leash from feeling that all these protons are pulling really hard on it. So as you the electronegativity increases as you go to the upper right hand of the periodic table. And so if you look up here, we see one of the atoms that comes up all the time in organic chemistry and biochemistry. We have oxygen over here. So oxygen is really electronegative. It has a tight pull on its electrons. What about hydrogen? Well, hydrogen, it only has a single proton. It cannot pull very hard. And so hydrogen is not electronegative. What about carbon? So carbon is over here. So you can see that it's in the same row as the oxygen. So you have the same like amount of shielding or whatever. So we're not going down the table, but it has fewer protons, so it's going to have a weaker pull. So oxygen is going to be more electronegative than carbon. Nitrogen is also more electronegative than carbon, but not as much as oxygen. And so these are the main types of elements that we're going to be dealing with in biochemistry. And the reason why I'm telling you about all these electronegativities is that it's going to affect the oxidation state, or basically who is going to own the dogs in the relationship. So basically the atoms are going to want to they can form bonds to form molecules. And so we've been talking about the atoms kind of like on their own, but the atoms can also like join together, and they often join together because they want to have like that full outer, this full valence shell of electrons. They want to be like these noble gases. And so they can share pairs of electrons to form a single bond, two pairs to form a double bond. They can also give and take electrons, but whether and how like willing they are to do this is going to depend on like the electronegativities and stuff, and whether they really want more electrons, whether they want fewer electrons. And then when they join to form a bond, when they when they form the bonds, so remember these electrons, we're drawing them in these like shells, but they're really in these clouds. And the clouds, when they share their electrons to form a bond, then you can think of the clouds as kind of like merging. But remember, there are these clouds. The electrons are whizzing all around. They're not held in place like the protons are held in place. So the protons are held in place, but the electrons can move more freely. And so when you're in a shared bond, they can move further towards one or the other of the atoms. So of those protons, like of the protons, so the dog walker is like stuck in place, and then the electrons, the dogs are running around. Are they going to run it when they're in this bond? Are they going to run, like, are they going to stay more towards one of the owners, like one of the atoms, protons, one of the nucleuses? And so yeah, so I'm going to I'm kind of going back and forth between like atom and nucleus. So the electrons are kind of like, we can think of the electrons as kind of being like joint custody between the two. And so when I'm talking about atoms, I'm usually talking about like in terms of where the proton is, like who's the owner, or who's pulling the leash. And so if you have leash pullers with different powers when you form a bond, then this gives you something called polarity. You have a polar bond. So if you have if you have like two of the exact same thing that bond together, they're going to share they're going to share their electrons evenly. But if you have some things that don't share fairly, then they're not going to share equally. And so this is what happens when you have a difference in electronegativities, such as between oxygen and carbon and between oxygen and hydrogen. And we can describe, we can use this term called an oxidation number to kind of say like who gets more electrons. So so kind of like if you were to split the molecules, so if you were like theoretically split these molecules, so you're not actually splitting the molecules, but if you were to split them, who would get to keep custody of the electrons? And so it's going to be the more electronegative one. So as we were talking about before, oxygen is really electronegative, and it's more electronegative than hydrogen. So if you were to form a covalent bond, so a bond where you're sharing electrons, if you were to form one of these bonds between between a hydrogen and an oxygen, then the oxygen is going to hog the electrons more. And if you were to split them up, the electrons, so like these dogs are going to stay with the oxygen because the oxygen is better able to woo the dogs. It's kind of like in the movie Annie, where like, she's like calling the dog, and the dog has to decide who to go to, and the dog runs to Annie, and it's this happy scene. So you can think of it like that. These dogs are going to stay with the oxygen. So, but this is not actually happening. We're not actually splitting these up. We're just thinking about what would happen if we did split them up. If we did split up something that was like a fully covalent bond, so not a polar bond, something that has equal electronegativities. So we're talking about like atoms between the same element typically. So here, if you have like H2, you have diatomic hydrogen, two hydrogens, they both, even though they're both pretty bad at convincing their dogs to love them and stay with them, they're both equally bad at it. And so if you were to split this bond, one electron would stay with each of them. So that's the basic theory, but where did these numbers come from? And so these numbers, we can determine in order to keep track of like who's getting or losing dogs or whatever, like if you were to form a bond, like where would those electrons hanging out with more? We can describe this number called the oxidation number. And so basically this is saying what would the charge be if they were to split up. And so we've been talking about these like hypothetical charges. But if they were to actually split up, they would have real charges. This is because the number of electrons, the number of protons is set, but they'd be gaining or losing electrons. And so in a neutral form, you have an equal number of protons and electrons. But if you were to, because protons and electrons are equal but oppositely charged. So if you were to be neutral and gain an electron, now you have one more electron than proton, you would have a -1 charge. If you were to lose an electron, now you have one more proton than electron, so you would have a +1 charge. So if we were to split these up, well, if we were to split up the hydrogen, well, hydrogen has 1 proton and it still has 1 proton, and 1 electron, and so it has no charge. So this is an oxidation number of 0. If we were to split this water though, now the hydrogen would be losing, it would have no electrons. So it still has 1 proton, but it has no electrons. So it's going to have an oxidation number of 1. The oxygen, on the other hand, it's going to gain 2 electrons because it gets to keep those electrons that it was sharing with the hydrogen. And so now it's going to have an oxidation number of -2 because it has 2 more electrons than it has protons. So sometimes this sort of like splitting actually does happen. And when this happens, we can have an ionic bond. And so with ionic bonds, now we have formal charges. And so these formal charges, before when we were talking about these, we were talking about like hypothetical charges. We weren't actually splitting these up. And so the oxidation numbers are not like the same as like a real charge because we're not actually separating them. But sometimes you do actually separate things and to form ions. If we look at our periodic table and we go back to the idea of like the number of valence electrons is equal to like the column number, and we were to look, and Na would be up here, so we can see that it has 1 valence electron, and chlorine is over here, so it has 7. And remember, they want a full outer shell. So sodium has a full shell below it. And so if it were to lose 1, it would have a full shell. And if chlorine were to gain 1, it would have a full shell. So that would make them both happy, right? So if in order to do that, so chlorine is going to have gain an electron, and this is going to, and sodium is going to lose an electron. If we lose an electron, then we're going to increase our oxidation state. And if we gain an electron, we're going to lower our oxidation state. And because they're actually doing this, like giving over custody basically of this electron, now you're actually going to have a formal charge so your formal charge is going to actually be the same as your oxidation number, because remember the oxidation number was a theoretical, like if this were to happen, what would your charge be? And then with an ionic bond, we're saying, okay, this actually happens. So this actually happens. Now you're losing an electron and you were neutral. And so you're going to have a -1 charge. You're gaining an electron and you were neutral. So you're going to have a +1 charge. Now you have a positive charge next to a negative charge, and opposite charges attract. So you're going to get these hanging out really close together. And so this is going to be like an ionic bond. So it's really just like a strong charge attraction. They're not sharing those electron clouds, but it is a strong charge attraction. Unlike like partial charge-based attractions. What if we were to look at like bigger molecules? So we can think of kind of like a poker analogy where you can look to the group number, so like the column number, ignoring the like the center part, the weird like part. If you look at the main groups of these column numbers, this is going to tell you how many valence electrons it has in its neutral form. And so if, for example, hydrogen and sodium, they both have 1. Carbon has 4. Oxygen has 6, and chlorine has 7. So this is kind of like what they start with when they're going into a bond. But remember, they can give and take electrons. So they can lose those poker chips, those electrons. So now we're switching from our dogs to poker chips for a minute, okay? And the reason why I'm doing this is because in biochemistry, often we're actually like molecules get reduced, so they get like oxidized or reduced. The reason why I'm doing this is because often in biochemistry, like in metabolism, molecules are getting oxidized, so they're losing electrons and we're gaining energy. And so you can think of it as kind of like coming in to a poker game. And so basically when we do in like metabolism, so when you're like breaking down, like metabolism is just like breaking and forming molecules. If we break down sugar, such as in glycolysis and do oxidative phosphorylation, we're getting a bunch of energy in the form of ATP. But we're getting this energy by passing electrons along a pathway, ultimately ending up in like the mitochondria, where you have this electron transport change where you're actually like passing the electrons. And so you are oxidizing those molecules and then transferring the electrons, and we'll get more into this later. But then but basically you have this transfer of electrons coming because you took a molecule that was in like a reduced form and you oxidized it. So oxidation is loss of electrons, and so you're losing electrons along the way. And so you're losing these electrons and you're funneling them in to this ATP synthase that can then use this flow of the you're using this flow of electrons to pump out protons, which then you can use the flow of protons to make ATP. But basically, all of this is coming from, you started with the molecules that you were then oxidizing to get those electrons to use in this pathway. And so you can think of those electrons as kind of being like poker chips that an atom can come into a reaction with. So if we want to determine the oxidation number, so we can determine the oxidation number of every atom in a molecule. And so the valence number is, so you have the valence number in its neutral form, which I'm going to be representing with these like white chips. Then how many it would own if the bond were ionic? Remember, this is our oxidation. How many it would own if the bond is ionic? So if we have a valence number minus how many it would own if it were ionic, that's how we get our oxidation number. Remember, because this is like what the charge would be. And so you have the valence number, so that minus how many it would own if it were ionic gives you the oxidation number. So this is like what it would be charged if they were to actually split up these molecules. And so if we look at, so like formic acid, if we were to look at formic acid, so let's look at this oxygen. So this oxygen is double bonded to this carbon. So there's 4 electrons hanging out shared between them. But oxygen is more electronegative than carbon. So if these were to split up, the oxygen is going to keep those electrons. So it would own this many electrons. It would own 8 if they were to split. They're not actually splitting, but if they were to split, it would own 8. And it has 6 to begin with. 6 minus 8 equals -2. So this oxygen has an oxidation state of -2. Okay, what about this oxygen? So this oxygen, it is bound to a single bond to a carbon. So there's 2 in this bond. So let's start with that. So oxygen is still more electronegative than carbon. And so this oxygen is going to get to keep both of these. What about with hydrogen? Oxygen is more electronegative than hydrogen, so it's going to get to keep 1. And so this oxygen is also going to have an oxidation number of -2. Okay, what about this carbon? So here we already said it's going to lose these guys to the oxygen, and it's going to lose these guys to the oxygen. But it's in this bond to the hydrogen, it's going to get to keep those. So it came in with 4 electrons. And now it's only, if it were to split, if all these were to split, it would only get to keep 2. And so it's going to have an oxidation state of 4 minus 2 is +2. And so it has an oxidation state of +2. Okay, what about the hydrogens? Well, remember the hydrogens are basically really bad at this game. And so only if you have 2 hydrogens bond to one another would they actually have an oxidation state of 0, where you would keep keep the same number that they came in with, which is 1. So whenever they're sharing a bond to something else, they're basically losing their electron. And so you are going to have a charge of 1 minus 0 is positive 1, so plus 1. So those oxygens have a plus 1. Another important rule is that the sum of the oxidation numbers should equal the formal charge. And so this, because you have, like, if you were, remember, this is like hypothetical, like if they were to split, who would they go to sort of things. But you should always, like, you shouldn't be having more go to something than there was actually some things or whatever. So yeah, so you're always, if you're, it's a good way to check your work. The oxidation numbers, the sum of them should equal the formal charge. So if you have a neutral molecule, that should be 0. This also helps explain why you always have oxidation and reduction go hand in hand. Okay, so if we look at, we can see that, as we kind of just were alluding to, when a hydrogen is going to, when a hydrogen is involved in bonding to something else, then it's typically going to basically lose. And so it's going to end up being oxidized. So it's going to lose electrons. Oxidation is loss of electrons or electron density, because, like, who hangs out with more. Reduction is gain in electrons or electron density. So reduction is like you get to keep more of the electrons when you share to something. So if you form a new bond to something and you get to keep more of the electrons, then you are getting reduced. If you form a bond to something and you lose electrons, you lose some of the shared electrons. So the other atom is better at hogging it, then you are going to be oxidized. So oxidation is loss of electron density. Reduction is gain of electron density. If something is bonding to a hydrogen, we said that hydrogen is like really bad at this. So if something bonds to a hydrogen, it's kind of like getting free electrons, even though it's also getting the hydrogen. So even though it's also getting the proton, so even though it's also getting like the hydrogen's proton, it's also getting the hydrogen's electron. And so proton plus electron neutral. So if you add like a neutral hydrogen, now what you're doing is you are still going to be kind of gaining electron density. So we typically, if something is a good rule of thumb, but not always true, is that if something gains a bond to a hydrogen, it's going to be, we say it's being reduced because reduction is gain in electron density, and hydrogen is really bad at sharing or at keeping its electrons. So it's kind of like getting free electrons. So this is why hydrogen, the gain of a bond to hydrogen is often accompanied with reduction. So for example, when you go from methanol to formaldehyde to formic acid, this is an oxidation, and going in the other way is a reduction. And this is associated with decreasing. So if we were to look at the carbon, so we can see that this carbon here, it is 1 bond to hydrogen. Here it has 2 bonds to hydrogen, and here it has 3 bonds to hydrogen. So it's getting reduced as it's gaining electrons. As it's gaining bonds to hydrogen, it's also like gaining electron density because the hydrogen's so bad at sharing. It's going to be kind of like it's going to get to hog more electrons as it's forming these bonds to hydrogen, and thus it's being reduced. Conversely, if you go the other direction, now you are going to be losing bonds to hydrogen and gaining bonds to oxygen. And so here you're actually gaining like another oxygen. Here you're just going from a single bond to a double bond. And so remember that the oxygen, when it's bound to a carbon, it's going to get to share all of the electrons. It'll get to kind of like keep all of the electrons in the bond if they were to split up. So if you have a single bond, that's only 2 electrons. So the carbon would only lose 2 if it were to split. But if you have 4 invested in that bond, now you're going to lose 4 electrons. And so this is why if you form more bonds to oxygen, you are going to be being oxidized. So oxidation often, but not always, involves the formation of more bonds to oxygen. So this could be like adding another oxygen molecule or just forming like a double bond instead of a single bond, etc. But so oxidation often accompanies the gain of oxygen, but not always. And reduction often is accompanied by the gain of hydrogen, but not always. And of course, redox, so reduction and oxidation come hand in hand. So if something's getting reduced, something is getting oxidized in the process. And so that's so often when you learn about oxidation reduction or whatever, a lot of times it feels like metals and stuff, and sometimes you just have like electrons are kind of actually like flowing in electricity and all of this stuff. But most of the time in biochemistry, you're talking about things being transferred from like one molecule to another, and you're talking about like this electron density instead of like actual individual electrons being transferred, which is why things can sometimes get pretty confusing. Another reason why things can get pretty confusing is because we talk so often in biochemistry about like protonation and deprotonation. And so with protonation, you're actually losing or gaining. So protonation, you're gaining, deprotonation, you're losing a proton. So just the hydrogen's like nucleus, not the electron. So remember, hydrogen only has a single proton. And so in its neutral form, it has a single electron. But if it were to lose that electron, now you just have a proton. And so we can use these terms interchangeably, proton and like H plus. So yeah, so in its like normal usual form, hydrogen doesn't have any neutrons, and so that's why it's just a proton. But anyway, if you lose or gain a proton, that's not going to involve any electrons. So when you gain or lose a proton, you're not changing the oxidation status, you're not changing it. And so when you go from formic acid to formate, where you're just doing this deprotonation, you're not changing any of the oxidation numbers because you're not losing an electron, you're just losing a proton. And so we can, we go back to our dog analogy. So if we have like this OH group, we can say like, okay, so if we were to hypothetically split these, then the electrons would stay with the oxygen. So if we were to actually split these, the electrons would stay with the oxygen. So the oxidation state is like, if this were to happen, what would it be? If it actually happens, what would it be? They'll be the same thing. So you don't have any change in the oxidation state with deprotonation. But with a hypothetical, you don't have like, if a change in oxidation state does not happen with deprotonation or protonation. If you want an oxidation state to change, now you have to have a dog and not just the walker leave. You need to actually have the electron leave or get swapped with something that's harder to woo. So when you have like deprotonation, you don't have the dog leaving, you just have like this walker leaving. And if you have like, so you can have like, if a hydrogen with an electron were to actually leave, now you would be actually having an oxidation state change, because now the hydrogen's actually keeping its electron, and before it was having to give it over to the oxygen. And if an oxygen per se is bound to another oxygen, so usually when oxygen is forming bonds to things, it gets to keep the shared electrons. But when it's bound to another oxygen, now they have the same strength of wooing the dogs, and so the oxygen has to share fairly, and so the oxygen can get oxidized. So one place that this can get confusing too is in biochemistry when we're talking about like these transfers of electrons. And so we talked about how like protonation and deprotonation does not mean like it's not changing the oxidation state. But then you look and you see, okay, so we have like one of the main electron transporters in the like in our metabolic pathways is NAD plus, which can become reduced to form NADH. And so we're like, okay, well, we're gaining a hydrogen. So, but we're not protonating it, but we have this charge. So remember, like a proton is positively charged. So NAD plus, is the oxidized form, is actually positively charged. So if you were to just gain a proton, you'd have a +2 charge, but we're actually reducing the charge here. So even though we have a charge change, we're actually reducing the charge. And so it can get kind of confusing because we're gaining like a hydrogen and 2 electrons, a proton and 2 electrons, so like a hydrogen and an electron. And so this is why this is actually involving reduction, and not like a protonation. And similarly with NADP plus and then NADPH. So remember, you're losing a charge, so you must be having, you're not adding a proton, you're adding, you need to be adding a negative charge. You're adding that negative charge through the electron that's actually being transferred. And then you could use these transfer molecules to pass those electrons in a series of redox reactions to power the flow of protons out of the mitochondria, and then like kind of like a dam, flow through and power this pump. Another common place where you will see redox come in biochemistry is with cysteines. And so cysteine is one of the amino acid letters. And it has this thiol group, so this SH, so it's the sulfur equivalent of an alcohol group. So an OH group is an alcohol, and an SH group is a thiol. So if we go back and we look at our periodic table, we can see that sulfur is under oxygen. And so it is going to be slightly less electronegative than oxygen because it has more shielding between its dog walker and its electrons, but it's going to also be electronegative because it's over here towards the right of the periodic table. So if sulfur were to like bind to a hydrogen, it would get to keep the electrons that it's sharing in that pair. But if sulfur is bonded to another sulfur, now it's going to have to share more those electrons, and so it becomes oxidized. It's losing electron density because it's not getting to like pull, it can't hog the electrons from the bonds like it could when it was bonded to hydrogen. And so this is why we can get cysteine when it forms these like cysteine, or I don't, it's really weird. Like I've never heard anyone actually like pronounce them or whatever, but like these cross links between 2 cysteine molecules on these like disulfur bonds. So here, when it was bound to a hydrogen, it was getting to hog the electrons in that bond. When it's bound to another sulfur, now it's going to have to share fairly because sulfurs have the same electronegativity, and so they're going to have to share fairly. And so if they were to break up, they would each get 1 electron in their shared bond. But if cysteine were to break from a hydrogen, it would get to keep both electrons. So in that sulfur hydrogen bond, the electrons are hanging out more with the sulfur. But in a sulfur-sulfur bond, well, they're both sulfurs, so the electrons are going to be hanging around both of them. And therefore, when you form one of these bonds, it's an oxidation reaction. And when you break one of them, it's a reduction reaction. And note that we can also go from the thiol to the thiolate state. That is just a deprotonation. And that deprotonations, remember, do not involve any transfer of electrons. And so that is not going to affect the oxidation state. But if you form one of these crosslinks, that does affect the oxidation state. You can also affect the oxidation state of a cysteine by forming more bonds to oxygen. And so oxygen is more electronegative than sulfur, because remember, it has less of the shielding. And so it's going to be able to hog the electrons when they share a pair. So if it forms more bonds to oxygen, it's going to be basically losing electron density because now it's having to share those with the oxygen, and the oxygen doesn't share fair. So cysteine is really cool because it can form like these cross links. And so this can be like between different parts of the same protein, between different proteins. We can add like chemicals to get them to link to other stuff, all sorts of cool stuff. And in the lab, we often have to worry about cysteine. So if we're doing like an SDS page gel, so we want to like denature or defold proteins in order to run them on a gel, we have to add, we typically add like beta-mercaptoethanol or something, some reducing agent in order to break these bonds. And so those reducing agents or antioxidants in our bodies, like glutathione. In the lab, we use like DGT, BME and stuff. So our cells maintain like a reducing environment inside of them so that we don't have these crosslinks forming, because you don't want these crosslinks forming between like random things or whatever. But often like extracellular proteins have these crosslinks that help keep them sturdy. But in our bodies, so like glutathione is able to act as an antioxidant, helping, so this can then get reduced by oxidizing glutathione, and then this gets recycled and you have this whole big cycle thing. But yeah, so that's a common place that you will see oxidation and reduction in biochemistry. And so like typically, because our cells maintain this like reducing environment, when we're purifying proteins and stuff, we typically add a reducing agent like DGT to our solutions when we're purifying proteins in order to keep them in like a physiological type environment. And so we don't form those like cysteine crosslinks that we wouldn't want.